अस्मिताने केलंय सुरू. आधी तिचा फोन एंगेज येत होता, पण केलंय अवदर अवदर. हॅलो महाल मॅडम.
हॅलो. गुड इव्हनिंग सर.
गुड इव्हनिंग, गुड इव्हनिंग. चला, तुम्ही तरी जॉईन झालात म्हणजे
हो
लेक्चर होईल आजचं.
हो.
विल वेट फॉर 5 मिनिट्स. अजून सव्वा
येस.
5 तासही व्हायचे आहेत. झालेत
शुअर.
आत्ता.
शुअर सर, शुअर.
5 मिनिटांनी सुरू करू आपण.
हो हो, चालेल सर.
Hello, Sagar. Are you able to see my screen?
Yes, sir. Your screen is visible.
Okay, okay. Okay, now without waiting for much more time, it's already 5:17, so we will begin our session. Just minimize this. Okay, today's topic is cogeneration. If you are already aware what is meant by cogeneration, it will be easier, and I am sure you must have read this chapter before attending my session. Anyway, my attempt is to clear all concepts If you have got any ambiguities, difficulties in understanding, we will clear that. Otherwise, the chapter is very simple to understand. In this chapter, we will be looking at definitions, needs, applications, advantages, classification, and all these things related to cogeneration. What is the need for cogeneration? Remember, simple thing. We want to increase the efficiency of heat utilization. That is why there is a need of cogeneration. What I mean to say by that is, you already know that when we use heat for power generation, only for power generation, there is no other intention. In that case, the loss of heat to the atmosphere is to the extent of 65 to 70%. Hardly 30 to 35% heat is converted into electricity when we want to use heat for power generation. Power means the electrical generation. Now, what about this 70% heat which is going to the atmosphere? Because a power plant which is constructed with the technology with the only aim of producing power does not have any alternative use for this heat which is being lost to the atmosphere. If we think of using this 70% heat which is already wasted, if we can gainfully or usefully utilize this for some other purpose, which is a useful work. For example, in a industry, small scale or large scale, you have requirement of steam. You need steam for so many processes, heating process, cooling process. Then there are regenerative purposes. So if we can use this remaining heat for drying purposes, generating steam purposes, providing steam for certain processes, then the entire heat which is generated by burning the fuel is used. Wonderful. Then that case, the efficiency goes to 85-90%. Right? Then comes the question, if we need electricity as well as the heat for the industry, a composite purpose, double purpose, then the same fuel which is used for generating the heat, partially the heat can be used for generating electricity at a poor efficiency of say 35%, and the wastage heat of the electrical process can be utilized 100% into the process steam purposes. So if you take the together efficiency of the system from the fuel burning to the useful heat, your efficiency improves. That means how do you anyway calculate efficiency? Efficiency of any machinery, system, power plant, or say industry. It is always the useful product in the numerator and the total consumption of the heat in the denominator. That means heat gainfully utilized in the numerator divided by the heat generated by the fuel burning. The ratio gives you efficiency. In only electrical operation, electrical generation equivalent of heat is only 30% and total heat is at the bottom. So efficiency is 30%. But if I can use 80-85% of the heat generated by the fuel, then the numerator will be greater, denominator will remain same because the same fuel is used. There is a efficiency improvement. The figure which I am showing you on the screen gives you a heat balance when heat is generated only for electricity. You see, fuel is burned in a boiler, then the boiler is generating the steam. The conversion of heat of fuel to the heat of steam is better. It is about 85% if you look at this boiler. in this boiler, the input energy is by burning the coal here, say 100 GJ. You assume any units, 100 GJ, 100 kilocalories, 100 million kilocalories, etc. And then the losses are accounted here. For example, energy loss because of the hot surfaces, energy loss from blow down to the boiler. That means periodically you have to remove the concentrated silt into the boiler going to the atmosphere. Then the steam generated goes to the steam turbine. Steam turbine rotates and rotates a generator. The steam condensing goes to the condenser. So in generator, the steam heat partially is used for rotating the generator and remaining goes to the condenser for again liquefaction of the steam into water. This heat, which is taken out by the condenser cooling water, goes to the cooling tower. Here the temperature goes down and the heat is going to the atmosphere. Chunk of it, major. See here, if the 100 is the input, the heat loss to the cooling tower is about 48. Right? You got it. Almost 48 to 50% goes to the atmosphere. Partially it goes loss here, here, here. If you take system as a whole, you will find the output of electricity here is 38, whereas the input is 100. So the base system which is shown here has a overall efficiency of 36%. You got the picture. Now this is heat balance for a typical coal-fired power station. These figures may change depending on the equipment is old, the technology is not proper, insulation is not bad, not good, and lot of heat losses are going here and there, the drains and this thing. So these 38 may ultimately result into 34, 35, or even 33. Now, if we change this picture by using the heat for the other purposes in the factory. Look here, the fuel has given you 100 units of heat. This 100 units of heat, what I am dividing, that I am generating 24 units electricity. I am dividing this between power generation 60% of the heat and heating the other purpose 40%. If I use it only for electricity generation, the blue diagram here, only 24% is used in electricity, remaining goes to loss 42%, that is going to the atmosphere. Instead, if I use a coal handling, that means CHP, that is combined heat and power, CHP, combined heat and power plant. Heat and power means same example, input is 100. So 124 and 42 is the loss with a 40% efficiency. Boiler loses 15% and all that. Here, this same heat generated, electricity 24, heat units 34, but the efficiency is improved because there is no loss going to the atmosphere. You need only 68 units of fuel. Here your fuel units were 100, here 68 with the same outputs, heat 34 and electricity 24. That means what? You have very efficiently used the heat fully and the loss here is only 10, whereas the loss here is 42. Overall efficiency improvement is there. The purpose of cogeneration is wherever it is possible to use the waste heat generated from electricity generation system. Instead of leaving it into the atmosphere, can we recover that heat in some other form? the more percentage recovery we achieve, more is the efficiency of heat utilization, right? So that is why the cogeneration is profitable and it is needed. Now, what are the technical options for cogeneration where we can use this cogeneration systems? One is a normal steam turbine. We will take the same example. Boiler is here, fuel is burned in the boiler, water is heated, converted into steam. The steam is let out into the turbine. Turbine is rotating the shaft on which a generator will be connected. This generator will generate electricity. Instead of throwing the output of a turbine, instead of the steam going to a condenser and letting out the waste heat to the cooling water, what we do, we do not allow the steam to go down to negative pressures or the vacuum pressures. No, we will stop it here. We will not extract the full heat of the steam for conversion into steam, electricity. Partial pressure and temperature steam will be given to a heating process, cooling process into the industry. This process means industrial process for which heat is required. So instead of going to the condenser, it will go to the industry. In the process of industry, heat will be imparted to the industrial product and the cooled steam that is converted into water goes to the boiler. So thereby we are recovering the waste heat of the turbine steam, which is the exhaust steam, allowing it to exhaust at higher pressure and temperature, collecting it for the process purposes and recirculating. This is called back pressure turbine. What is back pressure and forward pressure or zero pressure or vacuum pressure, negative pressures? You know, when the steam expand, it changes its state. Suppose I will give you the exact figures. For a power boiler, the steam pressure is as high as say 250 kg per centimeter square. The power boilers operating at say 650 megawatt capacities. But on an average, a industrial boiler has always a pressures around the 100 kg and the steam temperatures about 300 degrees centigrade or 250 plus. This 100 kg 250 steam enters a turbine and rotates the turbine rotor because of its pressure and temperature. But before this steam pressure and temperature goes down through the expansion to a vacuum pressure. Normally, for a condensing turbine, the pressure inside a condenser is vacuum. So the steam is fully exhausted into the condenser. If we stop, we remove the condenser, we give some pressure and temperature still there in the steam and then put a extraction. This is called extraction. Whereas in this diagram, this is called condenser. The steam turbine here is exhausting into a condenser. Condenser contains cooling water coils and this steam at negative pressure imparts its heat to the cooling coils and gets converted into water. This condensate form is going to the boiler, return to boiler. And the entire heat is taken out by the cooling tower. No, here what we are doing, we are not allowing it to be exhausted into condenser. Some pressure and temperature of the steam is extracted, goes to the process and then goes to the boiler. Right, this is one way. Back pressure. Here, a little modification in this system. In this system, there is no exhaust or no condenser. Here we want to get benefit of both these systems. That means we are partially giving it to the process and partially the steam is allowed to exhaust into condenser. Here the efficiency may be more. Here we are compromising the efficiency, but here we are allowing more electrical generation than here. Same steam, same pressure, temperature parameters. Here it is allowed to completely work for generating electricity and exhausted here. Here there is no electricity generation. It directly is exhausted to process. Electricity generation is partially, not full. Partially electrical generation, partially process work. Here also partially electrical generation, but here the quantity of electricity generation is more and smaller portion is going to the process. Since electricity requirement is more and the here requirement is less, what we do at the exhaust point, we allow it to go to condenser, but part of the steam before allowed to go to condenser is tapped here. This tapping is called extraction. This is the vacuum or the condenser exhaust. This is extraction, high pressure temperature steam. This goes to the process. It cools down. Here also cools down in condenser. Water goes back to. So these are two methodologies. One is purely back pressure turbine. It is not allowed to exhaust in condenser. Fully recovered heat in back pressure turbine. So wherever your mechanical power is required more than the electrical component, we use this system. So back pressure turbine system is the most efficient mechanical power system with the same amount of fuel. Here the efficiency slightly goes down, but it can give you a better power output and lesser output for the process, right? Then there are other possibilities also. Suppose you use a gas turbine. There we have seen a system with boiler and steam turbine here. Here it's a gas turbine. How do you improve the efficiency or recover the heat? See, this is fuel plus air mixture here. This part, gas turbine construction, you may see in the internet with good pictures. And since I am not having a blackboard to show you a drawing, I have to depend only on whatever diagrams given in this book. So this gas turbine frame contains half part as a compressor unit. This is showing the large diameter blades go into smaller diameter blade. That means air that is coming from this end is compressed and pressurizing this whole volume. Now, where the pressure is reached in this chamber, fuel is injected here and it takes fire. When it burns the flue gas, because it's a gas turbine, flue gas burns with a pressurized air chamber. This is called combustion chamber. And the gases with very high pressure will travel over these blades. This is a turbine, the right hand side. Smaller diameter going to larger diameter as the gases are expanding and getting higher volume. So the gases rotate the gas turbine and it is exhausted after the turbine. But the peculiarity here is the gas temperature at the exhaust is in the range of 500 plus. Many gas turbines are exhausting at 650 or 700 degrees centigrade. In steam turbines, we have seen the major loss point is the condenser, where the steam is giving out the heat to the cooling water. Here, major loss is through the exhaust of the turbine, which is a very high temperature exhaust. So, if we allow this exhaust without recovering the heat from the flue gases, we are making a loss, and the turbine efficiency may be as low as 35%. But what we do, we recover this heat from the flue gases. Instead of allowing them to go out, we divert those high temperature gases and use them as a fuel in a boiler, which is a ordinary steam boiler, as we have seen. The boiler here, right? Here the boiler is getting the heat due to burning of fuel. Combustion takes place here. And the combustion chamber, heat is transferred to the steam formation. Same activity happens here. The high temperature gases, they are circulated over the water coils, the water getting converted into steam, and this steam is then used either for the process or for driving a steam turbine, generating some electricity here. So you have a composite electricity generation, one on the shaft of the gas turbine. Here a generator is connected, producing electricity. Here a steam turbine, which is using the steam from this boiler, and the turbine is rotating the generator. So two places for generating electricity gives you maximum output possible of the heats. This is a gas turbine method of cogeneration. Here it is steam turbine method of cogeneration. Here in the steam turbine, the steam of high temperature and pressure is exhausted for process, right, after doing the work of electricity generation. Here the high temperature gases and not the steam are exhausted into a steam boiler, and the steam turbine is rotated. You got the difference between both systems. Then third system, in case of a reciprocating engines. A reciprocating engine used in a industry for some different purposes. One purpose is also for electricity generation. Reciprocating engines are not very common nowadays. They have been phased out. Rotary generators have come now, because we know diesel generators which already are using, they are not reciprocating. They are the rotary generators. But here, a case is when you are using a high capacity reciprocating engine. This is a reciprocating IC engine. IC engine uses petrol or diesel. It's the same system, no? It has a piston, a cylinder, and fuel is injected like your scooter engine, motorcycle engine, or the car's engines, or say bulldozer engines, all these big capacity engines. What we are doing there? We are compressing the air, igniting the fuel, the flue gases are exhausted. Likewise, in a reciprocating engine, there is a piston cylinder arrangement and it is generating power. But during the process, the cylinder, piston, and the mechanism of the entire machine becomes very hot because it receives at that temperature it is heated. So we have a jacket around the engine, reciprocating engine. What is that jacket for? One jacket is for cooling the heat. The heat is to be removed, because if we don't remove that heat, the lubricating oil will catch fire and no lubricating action will take place. So there is one lubricating oil cooler wherein the cooling water is circulated. Another is the air supplied has to be pre-cooled, because if we supply the air at pre-cool temperatures, the engine temperature can remain in control. So there is another air cooler. And third is the water input going through these jacket cooling water. So this small heat which we can recover from the engine is used for heating the water that is finally going to the boiler. So the steam reciprocating engines used earlier for power generation purposes were used like this. See, this is a boiler, fuel is injected, the boiler is converted into steam, the steam is utilized for process, the process cooled condensate goes back to the reciprocating engine. This reciprocating engine is already rotating a generator here. He has not shown it, but a generator. So power is generated here and the exhaust of the entire system goes to the process and the heat into this is fully utilized. The exhaust of this reciprocating engine gas temperatures are not as high as the gas turbine exhaust gas, but it is still high, about 450 to 400 degrees centigrade. So we can extract the heat from these gases, same purpose, the same steam generating coils are there in this boiler. There is no separate fuel for this boiler. Out of 450 degrees temperature, this boiler is absorbing around 250 and gases with 200 degrees centigrade are allowed to go to the atmosphere. Right? The heat is then used for process, cool down, goes back to the boiler for heating. It's a closed circuit for steam, this closed circuit for. Now here in reciprocating, this steam is not utilized for electricity generation, but it is only for the process requirement of the industry. Here, since the temperatures are very high, 500 plus, this temperature is used for running a steam turbine and generate the power. So gas turbines are normally used in cogeneration with the steam turbine. You got the point, remember this. So this system is called binary or combined cycle power plant, we can say. Why combined cycle? This is a gas cycle, gas plus air generating it. Another is the water cycle, water to steam and going back to. So it's a combined cycle. Gas as well as steam. This is a combined cycle with gas turbine. This is a single cycle. It's a reciprocating engine that is used. Then classification of closed generation systems. Simple thing. These are the terms which you will remember always because they will be asking 1 mark questions on this. What is topping cycle? The simple formula is when you are burning fuel generating heat, if the heat is first used for electricity generation and then used for process, like here, see what they have done here, first use for electricity generation in this turbine, right? Electricity generated and then the heat contained into the steam is used for process. This is called topping cycle. Topping means electricity at top and then other purpose at the bottom. Here it is also a topping cycle because here turbine is primarily used for electricity generation and the process steam is a secondary purpose. So remember, if the primary purpose is electricity generation, it's a topping cycle. Simple. No ambiguity in that. Right? So see here, a high pressure steam used for turbine, generator, power, and this low pressure extracted steam goes for the industrial process or some other purposes. So these are all topping cycles. This is a diesel generator. This diesel exhaust gases going to the process. First purpose is to generate power. Generator. It's generating power. Here also, first purpose is the generator, and then the exhaust gases of a gas turbine, they are used for some other purpose, either for steam generation, electricity generation again, or the system requirement, that kind. What is conversely bottoming cycle? Bottoming means when electricity is not the first product. First product or requirement is the process steam required for the industry for their own processes. And exhaust of that industrial process is used for electricity generation. Get the difference. First electricity, topping cycle. Afterward electricity, bottoming cycle. Bottoming cycle examples are, for example, in cement industry or the glass furnaces, where the temperatures required for the process are as high as 1000 degrees centigrade for melting the glass or roasting the gypsums and so on requirements. After doing that work in the factory process, the exhaust of that furnace, which is a very high temperature, 700, 800 degrees centigrade, that exhaust is used for heating the water in boiler. No different fuel is used. Only the exhaust of the process is used. Steam is generated. It is supplied to a turbine, a alternator, that means electricity is generated here, and the boiler exhaust goes to the chimney. Got the difference? So heat purpose is first process, and the exhaust of the process goes to the turbine. It is bottoming cycle. No confusion here. Right. Then factors influencing cogeneration choice. That means if you happen to visit a factory and they are already using the fuel, but their exhaust is going to the waste. So by auditing what is the heat content of the exhaust streams, you can suggest a suitable cogeneration system. Now, when deciding the cogeneration system, the industry need for electricity load as well as the thermal heat requirement of that industry, you have two choices. One choice is, some factory man says, sir, my basic requirement is electricity. I need heat for process, but primary importance is electricity. So you design a system for me in such a way that suppose I need say 1 megawatt of power. You design a plant, a generator which will give me 1 megawatt power. That is the base electrical matching. You match his requirement and the exhaust steam is then used for process. So you will have to suitably design the apportionment of the heat going to the electricity and going to the process. Now we have seen how this can be done. We have seen here in this particular picture. Here, this figure. That fuel is used in boiler. The steam apportioned to the turbine, steam apportioned to the process. Here electricity is generated. Here heat requirement is met. So if you design this system primarily to match the electrical load of the industry, it is called base load matching. That means what is primary importance? Electrical. You will design a turbine or generator in such a way that partially the heat requirement of the steam industry can be tapped from the turbine, and also it will be fulfilling the condition of generating certain amount of electricity. This type of option, when you fulfill as a energy auditor, it is called a method of base electrical load matching. Got it? Then conversely, When industry says, sir, my heat load is important, I need so much heat for the process. Electricity, yes, oh, you can vary it little. It's not very important. My importance is thermal load. Then you design such a system that the generator may be smaller, but you will pay attention for fulfilling the thermal load requirement of the factory. That is, heat apportionment will be more for thermal. Then third is electrical load matching. What is base electrical load matching and the electrical load matching? See, in this operating scheme, the facility is totally independent of power utility grid. In this system, what happens? The industry owner will say, sir, constantly I need only 1 megawatt, but occasionally when I start some processes, my electrical load goes to 1.1 megawatt, 1.2 megawatt. If you match the system only for 1 megawatt, in that case, this fellow will have to buy the power from grid, which is additional to 1 megawatt. Suppose his requirement goes to 1.2 megawatts. So 0.2 megawatt he can buy from the grid. But only that occasional rise and fall in the load, he should not entirely design his system for that because he has an option to buy from the grid, right? Here, this particular case, he does not have an option to buy from the grid. He wants to run his factory as standalone. He said, I will not be connected to the grid. You fulfill my requirements of a standalone system. Standalone means he will generate the full electrical power required by him. When he does not require that power, the heat will be utilized in the process. So heat utilization in process is flexible, whereas electrical loading as and when required, as and when quantity of electricity goes up or down, his electrical generator should be capable to take it. You got the difference now. No confusion. Now, thermal load, conversely, same thing. He wants to match his heat requirement always. If my heat requirement goes up, I should be immediately able to apportion that heat portion from your design. So give me a design which is flexible in heat load. Here, give me a design which is flexible in electrical load. Here, give me a fixed electrical load design. Any variation in the design, I will buy or sell from the grid. Same thing here. Basic, I need so much heat units constantly. If my heat requirement goes up, I will adjust my electrical load here, but I will continuously run this heat. So this is the only difference, thermal load matching and this thing. We will further discuss this point in next chapter. Now, important technical parameters for the cogeneration. What is the parameter? How do you design? Now look here at this. The table gives you heat to power ratios and other parameters of a cogeneration system. Back pressure steam turbine, the first diagram, where it is no condenser is there. No? Back pressure. Where is that? Yeah, it is here. Back pressure turbine. What are the components? Boiler, turbine, no condenser. Turbine, whatever it rotates goes to electricity, but chunk of the power at certain pressure and temperature, chunk of the steam, not power, steam is utilized mainly for process. Here the heat is completely utilized and it has got very high efficiencies. But here you will find that power component is very less and heat components is major used. So if I take heat to power ratio, right? What is heat to power ratio? Heat utilized and electricity generated. What is that? 4 times. That means heat in the numerator and power generated in the bottom denominator. If you take a ratio, you will find a large amount of heat generating a small component of electricity. So the ratio, if you take electricity to heat 4 times, matlab one time heat, uh, one time electricity requiring 4 times heat in the same units. That is electrical units, heat converted into electrical units, kW thermal, kW electrical. You read fully. I hope you have your books opened in front of you and you are also looking at what I am looking at the book and the same page. That will clarify your concepts. So, back pressure steam turbine has a high heat to power ratio. Whereas the extraction condenser, the same figure which I have seen, the adjacent figure, that partially it is used for power generation, partially for process. The power generated is more here, so the ratio is only 2. That means 2 heat to 1 electricity. When you go for gas turbine, it is still improved. Improved or the heat to power ratio goes down 1.3 to 2. Combined cycle, when you are fully utilizing, the ratio is 1. Almost the entire heat is used for power generation. Combined cycle. What is combined cycle? Which is explained here. Yes, this is combined cycle. That means the fuel which is injected into the chamber of a gas turbine is generating power. Also the exhaust heat going through the flue gases, it is also generating power, converting that heat into steam and steam turbine to generate. So here you will find with combined cycle, almost entire heat is converted into power. So if you take a ratio heat to power, the combined cycle gives almost 1 to 1. So reciprocating engine again the same thing, because here the process steam is the secondary, main production is electricity. So power output as percent of fuel input is minimum in back pressure, maximum in combined cycle and the reciprocating engines. There will be a question in, say, MCQs that what is the heat to power ratio, or whether the power output percentage of this particular case is so much, and you have to correctly choose it. Now, if you think efficiency wise, overall system efficiencies of back pressure steam turbine is the highest, and consequently they are different in different combinations, right? But you will find that the industries, which require this type of cogeneration, it is their requirement, isn't it? Their requirement for this, where is the thing? Yes. Yeah, different industries require different levels of the heat to power ratios. For example, breweries, pharmaceuticals, fertilizers, food, paper. Once your concepts of heat to power ratios are clear, then you will understand, depending on the steam requirement of that industry, you can design with a specific heat to power ratio. Cogeneration is likely to be most attractive under the following circumstances. What is that? The demand for both steam and power is balanced. That means consistent with the range of steam power output ratios that can be obtained from suitable cogeneration plant. If you can match the requirement of the industry for electricity as well as the process heat, then the best methodology is to design such a cogeneration plant that it will be completely matching with the load requirements of that industry. So this new factor I will like to again clarify. Energy utilization factor, EUF, is the percentage of useful output, that is a combination of electrical output and thermal output. Because in cogeneration there are two output, isn't it? Partially the heat is producing electricity, partially the heat is using for the process requirement. That is called thermal output. So formula says that heat equivalent of electrical output plus the heat going to the process together will form the useful output. This useful output upon the total input. What is the total input? Which is the heat energy supplied by the fuel burning. And how much is that? Quantity of fuel in kgs multiplied by the gross calorific value of that fuel per kg. That multiplication gives you total heat input to the process. And this input is producing what? The electrical output as well as thermal output. Electrical output is in kWh, that is the electrical unit. 1 kWh is equal to 860 kilocalories of heat. You can remember this formula always. Heat equivalent of 1 unit of electricity is 860 kilocalories. Plus the process steam which is given to the industry contains certain total heat per kg of steam. Calculate how much is that heat. So total kilocalories which are equivalent to electrical generation plus the process heat kilocalories divided by the quantity of fuel multiplied by the gross calorific value per kg. So it will be a complete ratio in the same units. This ratio is called energy utilization factor. If I can utilize complete units of heat provided by the fuel, then my energy utilization factor will be 100%. That means whatever is the kilocalories heat produced by burning the fuel is fully utilized, because the total of electrical generation equivalent plus the process equivalent is the same. But it never the case because there are many losses in the systems. The electrical output is the useful power generation from the turbine, and the thermal output is the useful extraction from turbine for process heating. The total heat will give you the flow rate by calorific value. Quality of thermal energy needed. What is the quality you mean? The quality of thermal energy required indicated by two parameters, temperature and pressure. This determines the type of cogeneration system. I will give you a simple example. We get solar heat, isn't it? But solar heat quality is so poor. Poor in the sense heat is there, but it is spread over on very large surfaces, on Earth surface. Geographically, if you want to collect it, it is not possible fully. You may collect from a certain area of say 1 acre, 4 acre, 5 acres. You can't collect it on a large basis. Again, the collection cost is very high. Infrastructure build-up or the solar panels or the solar concentrators, this kind of. So it's a poor heat. You can't recover such type of heat from a industry. When fuel is burned in a furnace, coal is burned, it raises a temperature of, say, 1100 degrees centigrade. If you want to raise the temperatures, you will have to go for higher heat incentive fuels like hydrocarbons. No, petrol, diesel, natural gas, they generate more heat. So depending on what is the temperature requirement and what is the exhaust heat that is going on, then you can suggest the cogeneration. If a very poor outlet, suppose you get a process exhaust of hardly 200 degrees centigrade, well, it is really cumbersome and not financially viable to recover a heat from a flue gas which is just 200 or below 200 degrees centigrade temperature. Similarly, steams which are only near the boiling point, say atmospheric pressure, if they are near the temperatures of 100, 110, 120, well, they are not worth for cogeneration. Cogeneration is commercially viable when the quality of heat available is much better. Secondly, the load patterns. When we thought of matching electrical load or matching the thermal load by cogeneration, this is the example, this is a load curve. What is the load curve? This is time from 00 to 24, right? 00 to 24. One factory A, what they do, in the beginning, when the factory starts in the morning, their major requirement is heat in the process, not the electricity. Electricity requirement is less. Major requirement is heat. Whereas in the afternoon, when this heat requirement is over, electrical systems are started and the electrical requirement goes up, whereas the heat requirement comes down. Why this happens? Because there are certain processes in a manufacturing, they require heat. So the first processes are heat processes. That time electrical motor load is minimum. Their electrical modes are not contributing. Heat is utilized. When this product comes to this stage after heat processing is done, and then the electrical refinement or machining work starts, there the electrical load increases. When you give a cogeneration system, how will you give for such factory? Right? You should have a more flexible cogeneration, which will give you double apportionment. In the morning, electrical steam going or the heat going to the turbine will be less for electricity generation, more for process. In the afternoon, more steam should go to the electrical generation, less steam for process. It's difficult to manage complex system. Whereas in a factory, electrical load as well as heat load, they go in parallel because their process of manufacturing product simultaneously requires heat as well as power. And therefore, all over the day, 24 hours, their requirements of heat and power are hand in hand. It is easier to give such a system by giving them a fixed apportionment of heat to power and heat to process. Right? So these are the load patterns, and then these patterns should be fulfilled as per demand by the cogeneration system which you are planning. Then what are the fuels available for this? Basically, how it started, whenever we thought of a heat going to the waste or the waste product that is thrown away. Take a case of a sugar factory. Sugar factory, after crushing the sugar cane, what remains is the biomass. No, that is called bagasse. This bagasse is a useless product so far as the sugar factory was concerned. They used to sell it as a fuel to somebody else, or the smaller industrial units will buy it. But then if they have their own yard full of bagasse, instead of selling it to somebody, if they use that as a fuel and operate a boiler, their own electrical needs can be met. Their own steam requirements also can be met with a free fuel for them because the fuel cost is it's a waste product. So it starts. So for sugar factory, fuel availability is the bagasse. For some other factory industries can use their own agro residue or the farm waste. There are many industries which are dealing with the vegetables, fruits, processing units. They, from their own agriculture fields, collect the biomass which is wasted. They dry it, use it as a fuel in their own boiler for steam generation. So depending on the availability of fuel also, the cost of generation or co-generation total as a system increases. Example here he says a rice mill needs mechanical power for milling and heat for paddy drying. So requirement is both electrical as well as the heat requirement. So rice mill has own rice husk as the biomass available as a fuel. So using the available fuels which are at cheaper cost and which are the captive fuels, they don't have to transport it from outside. They are the waste products of their own processes, can be used, and the co-generation becomes a profitable win-win situation. Then system reliability. Some energy consuming facilities require very reliable power and or heat. A pulp and paper industry cannot operate with a prolonged unavailability of process steam. In such cases, they need their own steam source and therefore they resort to cogeneration plants. Cogeneration, their both requirements are met. So depending on the availability of fuel, the systems can be designed. Then there are two type of systems, grid dependent versus independent systems, standalone systems. Again, the formula is same. Technology is the same, cogeneration. Grid dependence means you can design a cogeneration which is not flexible, rigid, and whatever variation in steam or the electricity requirement can be made from the grid. You can buy, nowadays the government is very flexible. You have got import export meters installed at your premises. So whenever you have surplus power, you can sell it, export it. When you need extra power than your capacity, you can take it from the grid. So you can have a very rigid co-generation system. There need not be a flexibility very large extent, right? Some base load requirements you should match. Then the third way a energy auditor should look at is retrofitting the existing system or giving a entirely new installation. Again here, what we will be looking at is the financial viability. For example, you must have seen in your boiler chapter that you may suggest as an energy auditor that you change over from a low calorific value fuel to a high calorific value fuel. Change from the wood boiler to the coal-based boiler. Change from a coal-based boiler to a gas-fired furnace or a diesel furnace, right? These suggestions are retrofitting suggestions. The installation is already there, but to match the same parameters, you change the fuel. Then how do you put up, how you make a proposal, the energy auditor putting a proposal for retrofitting? What are the basic concepts? Logically, see what will be the cost. The person, no, the industry owner will ask you this basic question. Sir, what will be the cost of retrofitting? How much downtime it will require for retrofitting from old to new? How much payback period I will have to suffer for this particular installation? And are there any substantial benefits in subsidies or in the government initiatives in this? So you have to prepare first the economic viability and the problems asked in paper 4 or paper 2 based on this system's retrofitting, changing the boiler fuel or changing the different pressures. No, your boiler is suppose a 100 kg boiler. Now you change it to 120 kg and you will get so many benefit. You will get extra heat or extra energy. So you will have to work out that. Then electricity buyback, as I already said, surplus buyback is allowed nowadays. Then local environment and regulation. For example, I am burning rice husk or burning coconut shell as a fuel or the biomass available, which is slightly moisture in that and it is giving a black smoke. So the location of the factory in which environment is there. Depending on that, you will have to change your recommendations. That means if it is in the heart of a metro city, well, they may not allow you to use that fuel. They will say you resort to, say, natural gas, because then the pollution will be less. They are not allowing you to burn coal or say the biomass, which is belching out a very black smoke. So these factors you have to keep in mind whenever you are suggesting some retrofit or a new system. Now, prime movers means what is the instrument used for cogeneration? Commonly is the turbine, steam turbine, gas turbines. Steam turbine functions you have already seen. This is a cutaway section. You can refer to the turbine chapter in this book only, paper 2. There it is given in more details. Here, the reference of turbine is only as a prime mover because the reciprocating engine as a prime mover is not very popular. Also, gas turbine as a prime mover requires a lot of investment, much larger than the steam turbine. Again, the gas is imported. It is not indigenously available easily. Whatever gas is available in the country goes to the fertilizer industry. So they will not be available for cogeneration. So the sturdy workhorse is the steam turbine. The turbine referred here gives you the idea of only so far as the extraction and the condensing turbines are given. The turbine control valve controls the entry of high pressure temperature steam in this chamber all around. This high pressure, high temperature steam forces its way and expanding on the way. It passes through fixed and moving blades. You imagine a blade rotating and one fixed volute which gives direction to the steam that is passing through. It creates a thrust on all these diaphragms and these are rotating. So the main shaft of the turbine is rotated. This rotating shaft is extended here and a generator is coupled to this shaft, giving power generation. This is the quantity of the generator producing electricity depends on how much volume of steam is allowed to rotate this shaft. If the entire steam that is entering is allowed to expand fully up to this volume, which is the last stage of the turbine blade, and exhausting into in this chamber, which is connected to a condenser below. That means this steam, high pressure temperature, expanding up to this, here the parameters are negative pressure and the temperature as low as 55 degrees centigrade, 45 to 55. Whereas here the temperatures are say 150 kg pressure, temperature is say 250 to 300 degrees centigrade. When the steam reaches this parameter, it is exhausted into condenser, cooled down, and the water is again sent to the boiler. Now, if you increase or decrease the quantity of steam, allowing to rotate this rotor, your electricity generation will increase or decrease. Suppose
Hello.
हेलो
एयर प्रोडक्ट एंड क्लाइंट है
हेलो
Hello. Yes, sir.
हाँ अनुजा एम आई विजिबल नाउ
अर्धो
Uh,
Not yet.
sir, no, no, not yet.
नॉट येट इज इट सो एकच मिनिट हा माझं बोलणं ऐकू येत आहे ना
Yes, yes, audible आहे, पण स्क्रीन नाही दिसत आहे.
एकच मिनिट इज इट विजिबल नाउ
Yes,
हेलो
sir.
Yes, sir.
मला खरं सगळं
नाउ इट इज विजिबल
Yes, sir, it is visible.
ओके ओके let us continue. Sorry for the disruption because the entire Chinsword software there is a problem. Is BSNL internet. Okay, so what I was talking, if this turbine is not connected to any generator, it is purely used for mechanical power or the process power, then this entire steam is used for the process, right? Sometimes the shaft is connected to generate and partially it is taken for the process. Many permutation combination. There may be one tapping for high pressure, one tapping for low pressure, depending on what is the pressure and temperature requirement of the process industry. So heat can be utilized at different pressures, different temperatures, and the balance steam is getting converted into electricity through the generator. So this is the very flexible and major prime mover, which is the steam turbine, which is not the case with the gas turbines or anything. What I explained is shown here in this diagram. The high pressure steam and extraction steams at different pressures. Suppose this is the high pressure steam going to the turbine and emptied at some pressure for the process and partially it goes for the generation. But it is not going to any condenser, it is going for the process. Here, in this first case, the pressure and temperature of the steam is fixed. In this case, I have two pressures and temperatures, steam is available. Requirement of the process is suppose only 5 kg, I will get a 5 kg steam here. If it is say 25 kg, I will tap it from this point and then use a 25 kg. If I am using it double extraction, right? This is first extraction higher, extraction 2, extraction 3. So we have a flexibility to get the steam at different pressure and temperatures as required by the process, right? The extraction condensing turbine, as I said again, we may lose some efficiency of heat but we get better generating capacity, and a partial steam is going for the process here. Extraction condensing. Here, this arrangement of gas turbine. The peculiarity of gas turbines is this. This is a shaft. This shaft is connected to a generator. On the same shaft, generator is there, same shaft, compressor is there, same shaft, turbine is there. The generator is electrical bound, it produces electricity. Compressor is different blades identical to turbine blades, and it is pressurizing the air into this combustion chamber where fire takes place and the fuel is injected. The high pressure gases of exhaust are rotating the turbine and exhausted on this side. The exhaust is not allowed to go to atmosphere as it is. It is diverted to a boiler, and the boiler will generate steam and steam turbine will rotate. So gas turbine is also flexible, but it is not as flexible as steam turbine. In gas turbine, there is no chance of getting different temperature flue gases. No, there is only one outlet for flue gases, and the steam generated out of flue gases, then you steam turbine, you can have as many connections. Right. That is the prime mover specialities. Then gas turbine efficiencies, remember this range of efficiencies you should remember because it will come in a MCQ for 1 mark, that without any heat recovery system, the efficiency will be as low as 35 to 40%. This is applicable to gas turbine. Right. Net turbine efficiency. What is the net efficiency? Above efficiency figure did not include the power consumed by air compressor. The shaft is rotated, the same compressor is consuming some power. It is not allowing to generate additional power. Fuel pump, other auxiliaries. The air compressor alone consumes 50 to 60% of energy generated. Right? This is what a bulk consumption by the air compressor. That is the lacuna or the drawback of this particular system. That compressor, which is a primary system necessary for compressing the air into the gas turbine, itself is a major consumption of the total energy generation. Then comes the reciprocating engine. You can read through, all these are only descriptions. Typical cogeneration performance parameters, they are given here. For smaller reciprocating engines, nominal range about 10 to 500 kW. Electrical generation is so many kilocalories, heat rate, the electrical conversion, thermal recovery, and overall. It is necessary to clarify this term, heat rate. Means what? Heat required per unit of electricity generation. Heat rate. Actually, 1 kWh of electricity is equivalent to 860 kilocalories. How much? 860. So, if the heat rate is 860, that means exactly by burning or generating 860 kilocalories heat, you should be able to produce 1 kWh. But in practice, you require 2650 kilocalories or in this range of kilocalories to generate 1 unit of electricity. So what is the efficiency? 860 upon 2650, hardly 31-32%. This is because of the system losses or the technology losses or the losses in condenser, losses in atmosphere, losses in leakages in the heat, right? So heat rate, basically remember, is always the heat required in kilocalories for producing 1 unit of electrical kWh, and the system which generates 1 kWh in minimum heat required is the most efficient system, right? So 2000 and above is the general common heat required per kWh, even in large capacity steam boilers for power plants, right? Remember what is heat rate. These are the different ranges by using different technologies. What is the heat required to produce 1 kWh of electricity? Larger gas turbines, smaller gas turbines, reciprocating engines and all that. Then relative merits of cogeneration systems. Read through advantages, disadvantages, what is the variation, fuel firing boiler, gas turbine with waste recovery boiler, combined gas and steam cycle with waste heat recovery. These are permutations and combinations of the equipments I have already described. What is waste recovery boiler? The boiler getting the heat from either the exhaust gases of a gas turbine or the exhaust gases of a glass furnace or a high intensity temperature gases into this. Also, okay, we'll go as per book, then I will explain. This steam turbine efficiency. What is steam turbine efficiency? Turbine cylinder efficiency is given as ratio of actual enthalpy drop and isentropic enthalpy drop as a percentage. Let us understand the concept. Actual enthalpy drop means actual heat loss when the steam expands to the a turbine blade stage. One fixed blade, one rotating blade forms a stage of a turbine. When steam passes through it, ideally without any losses, the heat loss per should have been a fixed quantity which is pre-decided. That is called the isentropic, ideally as per rule. But actually it loses more heat, right? And therefore the power generated is at lower efficiency or lesser thrust is created. That is the efficiency of a turbine. So what should have been the loss? If the loss is more, take a ratio of actual loss upon ideal loss, and that will give you the turbine stage efficiency. Now this definition, efficiency ratio of actual enthalpy drop versus isentropic enthalpy drop and take a percentage is the turbine cylinder efficiency, right? See, this is the graphical, this is the entropy enthalpy. Now this is the heat H1, H2 at point A. Point B, it is H2 minus H isentropic. Entropy, how do we cut? If this point H1, if you take a perpendicular drop on this axis, is here. It should have been isentropic. It should have been like this. Expansion should have been here. That is, after this stage, the enthalpy should be here. But in reality, it is here. The expansion takes place like this. It doesn't take place isentropic. Therefore, the heat is at this point. So efficiency is equal to A upon B. That means H1 minus H2 upon H1 minus H2. This is H1, this is H2, H2, and this is isentropic. So isentropic drop is more, whereas this actual drop is less. So the ratio, this actual drop A upon isentropic drop B gives you turbine efficiency. That is actual and isentropic drop. Just to clarify, here the values are not given and values will be given if the problem is there. You find out the efficiency of a turbine stage, they will give you all the three values. H1 value, H2 value and H isentropic value. These three values are there. What you have to do? Actual. This is H1 minus H2. Ideal H1 minus H2 isentropic. Take a ratio and efficiency. This may come as a question for 1 mark MCQ, or it may be a small problem 5 marks on that to calculate the turbine efficiency on the isentropic heat. Then turbine pressure survey. What is pressure survey? As I said, if this is the steam turbine we have seen just now here. Now this is a gas turbine. This is steam turbine. Now the pressure drop, that means the pressure here starting is say 150 kg, whereas here it is suppose 5 kg, or if it is condenser it is negative vacuum. The pressure is gradually dropping from full pressure to negative pressure. So in this journey from this point to this point, through number of stages, the pressure is continuously dropping. So you will have to know or draw a graph to indicate where, at what point, which pressure is there. Therefore, when you design, suppose the process requirement is 15 kg steam with 200 degrees temperature, you will have to find out the point where is the 15 kg. Here it is 150 kg. It will expand. Here it is suppose 15 kg. At this stage, you have to take out a bleeding of the steam to meet the process requirement. Again, if it is a 5 kg requirement, further go down, take another tapping for 5 kg. This method of measuring is known as a pressure gradient or pressure survey across the turbine. This pressure survey will enable you to find out the correct pressure and temperature steams available in that particular section. Where we were, turbine pressure survey. Very useful assessment of this. Then turbine heat rate. Heat rate, same meaning. To produce 1 kWh of electricity, how much heat input is required to a turbine? So it is expressed in kilojoules or kilocalories per kWh. The inverse relation between heat rate and efficiency is applicable only to a power plant. That means when the turbine is fully condensing and used only for electricity generation. Now, about cogeneration efficiency, how do we calculate? We can say by direct method, what is the total heat input by fuel burning? That is kilos of fuel multiplied by the calorific value of the fuel is the total input. What is the total output? That is the heat going to the process, heat going to electricity. So output upon the total input will give you the efficiency. There are certain exceptions to that. Being useful heat output by heat input is not necessarily inverse of heat rate. No. Heat rate calculations are based on the losses, how much losses we are losing. Whereas the overall efficiency of a cogeneration system directly gives you the useful heat outlet divided by the total input. Right. Now, cogeneration heat rate and efficiency assessment. How do you assess? A good example is given here. My request is all the parameters are given here. Turbine heat rate with 6 MW output normal proportion. Here, see, ready-made he has given you the quantity of steam 34.8 tons. When you are solving this example, you will have to convert these tons into kgs because all other parameters of heat etc. are per kg. Right? So it is 34,800 kg. The pressure is 64 at a 64 kg per centimeter square. 500 degrees centigrade is temperature. And at these parameters, the heat content per kg of steam is so much. Here the example is kJ, but normally in exam they will give you kilocalories. If you want to convert these, well, go to the joules and kilocalorie conversion factors which are given. So this turbine is connected to a 6 megawatt generator. Now, This is not fully utilizing this steam, but it has extraction 1 which is taken at a pressure of Q2. Pressure is given here somewhere. Yeah. Return administration. Heat is given 203 to return. Then here heat is given at this temperature. Quantity is given. So quantity in kgs multiplied by heat per kg will give you the total heat extracted from the turbine in this extraction 1. In this extraction 2, again, the total heat is given per kg and the quantity in kgs 35500, 3.55 tons, so much. And the exhaust steam again, what is the heat content of this and what is the quantity. So you can make a total of how much is the heat input, how much is the heat output. Calculate here, and calculate here. So the useful heat output is the total of these three heats. Input is this heat. You take out a ratio that will give you overall efficiency of a turbine. Got it? Because partially this megawatt also carries some heat. And for this, he has given a ratio 1 kWh is equal to 3600 kJ. He has made it simpler. You need not go and search for the equivalent formula. It is also given. See, the numericals will change. Only the data will change. Instead of 34 tons, it may be 40 tons, it may be 70 tons. Problem which will be there in the question paper will remain same, except the calculation figures will change. If you know the basic methodology, how to calculate the efficiency, there is no problem. You can solve any issue. So my request is you go to the problems which are already solved in the book. Understand them, try to solve yourself without looking at the book. If you couldn't solve it, go back to the book, find out what values he has taken up and how he has done the calculation. Go on repeating till by closing the book, you can solve your problem confidently. Yes, now I can solve. If you can solve this problem without referring to the book, then you are not worried whatever may be the values that may come. You will solve the problem. It's only a question of calculations. See, he has already given how to heat to power ratios, illustrations. Now, there is one slight variation to cogeneration. Cogeneration means normally two products from the same fuel burning heat. Fuel is burned only once heat is generated. If the heat is divided into two fractions, it is cogeneration. It is heat and electricity. But sometimes they have a requirement of trigeneration. That means third. What is that trigeneration? This refers to simultaneous generation of steam, power, and refrigeration through integrated systems. You know, the refrigeration also needs heat. Heat in the sense that there are different type of chilling processes. Now, a combined cycle tri-generation plant could typically consist of gas turbine generator, waste heat recovery boiler, steam turbine generator, and absorption chiller to meet 100% of the facility energy needs. Okay. For example, there is a cold houses or the refrigeration products are stored in a hall. So their requirement is also for refrigeration. So they need heat to operate absorbent type of chillers. So they will have only one single gas turbine. The gas turbine will be using natural gas. The gases out of it will be heating the steam boiler. That steam is operating a steam turbine, and the steam turbine exhaust or extractions can be used for process or for refrigeration. This is tri-generation. You can find n number of tri-generation sectors different in say medical industry, dairy products, dairy industry, or say even fertilizer industry. So these are only the uses of the same heat in different streams. Then there are some micro turbines. The concept is same. It is here the comparison is between a steam throttling valve and a steam turbine. So let us clear our concept. Throttling valve, what it does, it allows a high pressure temperature steam. It reduces the pressure from P1 to P2, right? And corresponding temperatures. But here the heat or the pressure reduction is achieved by throttling and it is not doing any useful work. The same function of reducing pressure is also taking place here. Reducing the temperature also taking place here. So instead of valve, you can use a small turbine. And the turbine shaft, you connect one generator. You will generate electricity. Very small quantity, of course. Very small, depending on what is the flow and temperatures available. But this is giving you some conversion of waste heat, which otherwise a throttle valve will only become hot and allow it the steam heat to go to the atmosphere. Here the heat will be converted into electricity. So pressure reducing valve versus a micro turbine. This system is more efficient because it is giving not only the desired reduction you want per process, simultaneously it gives you some electric power which is not here because here the heat generated is wasted to the atmosphere. That is the only principle on which it is working. So they will give a small example, pressure reducing valve versus back pressure turbine. What is the advantage? What you will get extra? Well, the same example, you try to solve it. But on this, there was no question in last, I think, 2, 3 years exam. But they may ask, you can be prepared to efficiencies on this. My request is all the solved problem in this book are typical and very explanatory. Every step he has given is fully explained. So if you are able to solve the same problems with the same parameters, same calculation independently yourself without referring to the book, you got the expertise to solve the problem. This exam, if you could solve at least few problems correctly, you will easily pass through because section 1, which is 50 MCQs, is there to help you in getting the bulk marks. Out of 50, if you can correctly write 35 to 40 MCQs, you get a bulk mark of 40 marks there. There is no deduction or nothing wrong. There is no negative marking. So you can take your chance and complete the entire 50 questions. If you could get 40 out of 50, remaining 35 marks from the remaining 100 marks paper is quite an easy job. If you solve 2, 3 problems correctly, write short notes, you get the necessary passing level of 75 marks. So don't worry, confidently you concentrate, spare some time in a day for dedicated time for studying this. Now briefly, in the remaining 10 minutes, we'll go through what are the, where is that? What are the MCQs he has asked? You are able to hear me? Hello?
Yes, sir.
Okay. Okay. Now, in fact, I will only read the question or refer the question and you have to answer. A cycle which generates first electricity is called, just now I told you, first electricity topping cycle, right? Next electricity first process, then bottoming cycle. First electricity topping cycle. Never forget this. A power plant which uses first a gas turbine followed by steam turbine for power generation is called, they are using two cycles, isn't it? Gas cycle as well as the water cycle. So it is called combined cycle. B it is. In the first question, it is also B, topping cycle, because first electricity is there. Here it is a combined cycle. For same inlet condition of the steam, which of the following will generate maximum mechanical power? Not electrical, huh? The total heat utilization, maximum. It is always the back pressure turbine, because it is fully utilizing. In back pressure turbine, a small component of heat goes to electrical generation. Bulk is used. There is no waste heat. Entire heat is used. Therefore, it is a back pressure turbine. The equipment having the highest efficiency in case of cogeneration plant is highest efficiency, no losses. It is the electrical generator. Because all other here, cooling tower, heat losses are going to the atmosphere. Gas turbine, we have seen it is less than ideal efficiencies. Boiler is losing a lot of heat. But electrical generation is the highest. Always 95, 98% electrical generators we have in the market. The efficiency of a standalone gas turbine without any heat recovery, all the heat going to the waste into the atmosphere, will be in the range of 35 to 40. You can go back to the paragraph, read through it again. I am just spoon feeding you here, but I don't like that. Actually, you should go from this each question, refer to the respective para on the particular page, then you will remember permanently. An axial compressor is used in conjunction of which of the following? Axial compressor is used in gas turbine. We have seen that. Almost 50% power is absorbed by the axial compressor. That is the case in only gas turbine, because other turbines are not using compressor. These are all steam turbines. Only the gas turbine needs a pressurized combustion chamber. Then next is a cogeneration system, is also known as combined heat and power system. In short, it is called CHP. A CHP means combined heat and power system. This chapter, in the first para itself, he says, when we talk of cogeneration, it is a combined heat and power system. The first para itself of this chapter. Power is generated from the waste heat of a sponge iron plant. Waste heat. That means first the fuel heat goes to sponge iron plant process, and the waste heat goes for the cogeneration. Which type of cycle is? Here, electricity is not the first. It is later on. So it is a bottoming cycle. If electricity is generated first and then heat is utilized for other purposes, then it is topping cycle. We have seen in the above question. But if it is for process first and the waste heat of the process goes for electrical generation, it is a bottoming cycle. Air compressor alone consumes 50 to 60% of the energy. Go to the respective para and read. If you remember, I have read the same percentages. A paper plant needs steam at 3 kg and 10 kg, two different pressures, in addition to electric power. The most suitable cogeneration choice will be extraction come back pressure turbine. Right? The extraction of the steam will be taken at, not back pressure, sorry, it's a condensing turbine with extraction. Extraction come condensing. Then match the following. You go to the chapter, I have just given you the table. Please go to the table. If you have got the book with you, go to the table and you tell me what are the parameters. Come on, we have got another 5-10 minutes with us. Can anybody volunteer? Hello, Pise? Or Anuja?
Sir, I don't have the book right now open with
Okay.
me.
One who has a book, can you open the book and see? I think you have already opened the book and you are referring to the book when I am talking to you. Okay, then do this exercise at home. I just wanted to take it. The exact figures are given in the book. Only the sequence is disturbed here. You will have to correctly check it. Right? Go to the table and find it out. Now here, two long answer questions are given, which are solved. Now here it is not solved. The figures are given. Based on the concept which I have told you and already described in the book, you can attempt these two. If you can solve this correctly, very good, you get some confidence in attending the problems. These types of problems based on this chapter are rare. Normally, these questions are more on the boiler and turbine performance evaluation case, paper 4. Paper 2 has got certain problem efficiency showing direct and indirect method or the calorific value GCV NCV method. So frequently you read through what was the questions asked on this chapter in earlier exams and prepare it accordingly, giving them some time. So with this, our chapter comes to close. Sorry for the interruption for 5-10 minutes in between, but we could complete it successfully. Right? With this, I wish to close this session. Any questions or anything you want to ask me? Hello?
No, sir.
Okay, then we will call it a day. We'll stop it. Okay, thank you attending. But let me see how many of you are there. Only 3. PC has already left. Anuja is there. Tutu, Suprita and Anuja. Okay, bye.
Thank you, sir. Thank you so much.
Thank you, sir.